So it is my pleasure to introduce you to Ross Street. Probably Ross doesn't really need an introduction. I'm sure everyone here knows him, but here we go. Ross is a founding member of the Australian School of Category Theory. He is known for his work in many areas of category theory, like formal category theory, enriched category theories, the theory of modules, and so on, many other topics. He is now an emeritus professor at Macquarie University and retired, but certainly that doesn't stop him from doing research full-time. And today he will be speaking to us about star autonomy and Mackey functors. Go whenever you are ready, Ross.
Well, thank you very much, Giacomo, and to your group for inviting me to this. And that was a very formal introduction, so continue on. Let me see. Yes. So I decided to talk on two topics, which will start quite independently. I'll talk about star autonomous categories as high dimensional Frobenius monoids, and then apparently start a completely different topic on Mackey functors as generalized group representations, and then tried to link them up, making the second a kind of example of the first. But the main reason for choosing these two topics is that I think it shows a lot of techniques that I've worked on and I've found helpful in category theory. And so I'm hoping that you'll get something out of it. So star autonomous categories, there was a Springer lecture notes volume by Michael Barr in the late 1970s, and it was mainly the main examples he had in mind were getting extending dualities in topological algebra, topological vector spaces, and so on. But there was a earlier mention of similar things by Grothendieck when he was at Harvard University, and that gets referred to in the Springer lecture notes by Hartshorne, which was quite influential on me, that Hartshorne volume, because it was where you could get information on triangulated categories back in the early days. And so the star autonomous categories are called by some people Grothendieck-Verdier categories. The other connection is that star autonomous categories seem to give the categorical version of Girard's linear logic. And Girard developed a diagrammatic calculus for that logic, and so you can use that in star autonomous categories. And the place we got into the act a little bit was that Brian Day and I related star autonomous categories to quantum groupoids. Trying to move, that's better. Yes, so the star autonomy comes in when you want the quantum category to become a quantum groupoid, although there are other things that are competing definitions there. And we also recognize that star autonomous categories were higher dimensional Frobenius algebras. So I'm going to start with talking a little bit about Frobenius algebras and show how that gets categorified. So Frobenius algebra is a K algebra where K is, let's say just K is a field for our purposes, because I'll just want to write vect instead of mod, because I want to use mod for some other purpose later. So we'll just suppose K is a field, and a Frobenius algebra is an algebra which is its own dual, and the kind of in the own dual in the monoidal sense, because every vector space has what the vector space people call a dual, which is the linear maps into the field, but that's not actually the monoidal dual unless the vector space is finite dimensional. So the extra bit of data can be chosen to be a bilinear map into the field, which acts like a a co-unit for the adjunction between A and A. And it has this extra property relating it to the multiplication that sigma of AB tends to C is sigma of A tends to BC, a very natural condition. So as I just mentioned, the existence of any monoidal dual at all for a vector space implies that the vector space is finite dimensional. And so the so-called dual space actually becomes the monoidal dual. And so in vector spaces, you have this candidate for being a dual anyway. So instead of saying the thing's its own monoidal dual, you can express it in terms of that actual candidate for being a dual. And you see that the formula, if you set A equal to 1, you see that you get a formula for sigma in terms of this epsilon. If you take epsilon to be sigma 1 tensor blank, we just get this little map into the field. And so that leads to the following definition in terms of epsilon of a Frobenius algebra. So I'm going to now move into a monoidal category V, and I say that a monoid which has object A with a unit J and multiplication P is Frobenius when it admits a right dual A star, which we're not in the first instance taking to be A itself now. So you need, so the unit that you're given then is called D, and then the condition that A should be its own dual is that that composite in terms of epsilon, another piece of data. So the extra piece of data besides having a dual is an epsilon going from A to I. I is the unit for the tensor product, which is the field in the case of vect. The condition is that that composite should be the identity. So you can actually categorify that fairly quickly, almost exactly the same definition. So I'm going to talk about a Frobenius monoidal. So monoidal is the word we're using now for a pseudo-monoid. Some places we've called it monoidal object in a monoidal category, but I like monoidal, which I think is like locale and quantile and so on. So a monoidal is in the monoidal bicategory now, M, consists of an object and a unit and a multiplication, which you usually call tensor product, but we'll call it P, and then an associativity constraint and a left and right unit. And you say that that is Frobenius, the monoidal is Frobenius when it admits a right bidual. And so that's what you talk about in, it only differs from dual in the fact that the equivalences, you have equivalences instead of isomorphisms. And so you suppose the unit is called D, and it's equipped with a morphism from A to I. That's the extra piece of data. And you want that composite to be an equivalence. So as just about in all my talks, I talk about modules. So let V be a complete, the type of monoidal category that Max Kelly has in his book as a base for enriched category theory. So let V be one of those. The book doesn't have much about, in the sort of implicitly talks about modules, but it doesn't actually talk about V mod. That's why I keep talking about it. So if you'd be happy, you just take V to be sets or take it to be vector spaces. So the objects of V mod are just the small V categories. And in those two examples, they're just ordinary categories and what people call K-linear categories, where you have addition in the HOMs or vector space structure in the HOMs. And the HOM categories in this bicategory V mod are these kind of pre-sheaf, enriched pre-sheaf categories. So I'm just thinking of V mod AB, the HOM in V mod, as an ordinary category. That's what that little zero there as the subscript means. So you take the enriched V functors from B op tensor A into V, and that's what I call a module, a left A, right B module. And you just think of that as an ordinary category. So the two cells are V natural transformations. So the objects there are called V modules from left A, right B. And composition is given by a co-end, which is very much like just the ordinary tensor product. You see, if we're talking about V being vector spaces, then the one object V categories are just algebras. And these are just, this is just tensor product of modules over the algebras. Is that clear? The identity module is, I somehow can't see the whole page. There I go. The identity module, which I might write as 1, there are lots of 1s in the world, is the Hom functor of A. And now V mod is actually a monoidal bicategory. It's symmetric when V is symmetric, and autonomous, we'll talk about that in a minute. So the tensor product of two V categories is just as it is in Max Kelly's book. The objects are just pairs of objects, one out of A and one out of B, and the Homs are given by tensoring the two Homs. And the unit for this tensor product is the one object V category, where the endo-Hom of that one object is just the tensor unit. Now V-mod's a pretty good place. It's a bit more like vector spaces than you'd expect than V-cat, because the co-product of categories, which is just the V category, is just disjoint union. It's easy to form. And co-product of in the Homs in V. So you need V to have co-products. But it's also the product in V-mod. So not only do you have, as in abelian groups, you have direct sums, where sums, finite products and finite sums, co-products, are the same. Here you have it for big ones as well. So you have all small direct sums. The big co-product is also the big product in the categorical sense, bicategorical sense. And every ordinary V functor becomes a module by doing that sort of covariant, putting it in the covariant position. So remember that a module, the way I'm taking it, is a V functor from B op tensor A to V. You could do it the other way, and there'll be people wanting to do it the opposite way, and I'll give a good argument why maybe the other way is good too, because I'm going to look at V mod op later. So these modules that are of the form F lower star, we say converge to F. So it's like, and this is all inspired by Bill Levere's treatment of metric spaces. And he showed that this really is related to sequences in a metric space converging to a point. Anyway, this gives you a pseudo functor. That means it's a functor, except that it just preserves composition up to isomorphism, not up to equals. Turning every V category into a, well, it's the identity on object. So every V category becomes a V module, but every functor now, V functor, becomes a V module in the same direction. And that's the reason I do the things the way I do here. And it's the only place where you lose information is on the modules, on the objects. It's locally fully faithful. So on two cells, it's an isomorphism. And it's also strong monoidal, preserves the tensor product and preserves the co-product. And this is where you actually have duals, and they're just the ordinary dual of a category. It's a kind of nice, in the old days, we used to write A up a star for for the dual of a category. And then the French were writing A up OPP, and then somehow in the English literature it became just OP, and that we call it the opposite rather than the dual. Anyway, the co-unit for that has got to go from A tensor A op to I, which is actually as a functor that goes from A tensor A op to V, and it's again the Hom functor just twisted or switched using the symmetry in V. You just apply that first, and then okay. Why is it not going on? Okay. So as I said, well, V is, oh, it's going on by itself. V, stop. Oh, it's become a slideshow or something now. Okay, there we go. So you say a module's Cauchy when it has a right adjoint in the bicategory. So that means the module exists going back from X to A and satisfies the sort of two-dimensional version of what it means for those things to be adjoint. The new one being on the right. So the convergent modules do have right adjoints, and so they are Cauchy. And you say that a V category is Cauchy complete when every Cauchy module into it is convergent. So there's Cauchy complete when every module is convergent. Every Cauchy module is convergent. Cauchy just means has a right adjoint. So the Cauchy completion consists of the Cauchy modules, the right Cauchy modules, you might call them. So it's a sub V category of the pre-sheaf category, X op V. Yeah, but as modules, they have right adjoints. You can say that in terms of the Hom from it, preserving co-limits and that kind of thing as well. So what I'm claiming is that any V category with the slightest bit of completeness or co-completeness is a Cauchy complete V category. When V is sets, of course, it's just idempotent completion. Idempotent splitting is what Cauchy complete means. And so big categories are Cauchy complete. The big categories of interest, maybe in homotopy theory you get some problems, but the big complete and co-complete categories we're used to will be Cauchy complete. And the small ones might not be, but if they're not, you just move to the Cauchy completion. And since you use small categories mainly for looking at functors out of them, it doesn't make any difference. The functors out of a category, a V category, are the same as the V functors out of the Cauchy completion. So in some sense, you can always consider them to be Cauchy complete. And in particular, equivalences in V mod are Cauchy because an equivalence anywhere has an adjoint. An equivalence in V mod is Morita equivalence, you might call it. It means that the pre-sheaf categories are equivalent. But if between Cauchy complete categories, it's just ordinary equivalence because the equivalences have right adjoints. So I hope that was clear. So Brian Day introduced, I think in his original paper, in his thesis, he called them premonoidal categories, but they've become called promonoidal categories because, well, that's a long story, but modules used to be called profunctors, and the pro comes from that use of pro. So anyway, monoidals in V mod op, because Brian Day wanted to look at functor categories in the form AV, the functors from A to V, and he wanted to make that a monoidal category and rather than A op V. And so that's why he's done it the way he did. But that means a little bit of a problem here because we've got to turn everything around and look at V mod op. So the tensor product for a monoidal in V mod goes from A into A tensor A, and the unit goes the other way. And as V functors, this tensor product goes from A op tensor A to V, and the unit goes from A to V. So if X is sufficiently co-complete, you can form convolution and get a monoidal structure on the functor category from A to X. The unit is just tensoring with the unit for the promonoidal category, with the unit for the tensor product for V. In X. I hope that's the tensor product here with the boldface J tensor I is the tensoring in the sense of a co-limit of something in V with something in X. Anyway, here's the formula. And when you have a monoidal V category, it becomes a promonoidal category using those formulas that I've got down there, which is really just saying that the J considered as going from I to A op, and the P is considered going from A op tensor A op to A op are convergent. So, if you had you would only have to say that they were Cauchy if you knew that everything's Cauchy complete. The A is Cauchy complete. So you can define a Frobenius monoidal V category to be a Frobenius promonoidal V category. Sorry, what am I? A Frobenius monoidal V category is a Frobenius monoidal in V mod op. So it's a promonoidal V category together with the N is instead of that epsilon, right? The epsilon went from A to I, but because we're in op, as a module, it actually goes from I to A, and you've got a certain composite that needs to be an equivalence. And if you calculate that composite using the co-n composition of modules, it gives you a module boldface S. I'm using boldface for the modules given by that integral, the co-end. And that means that you can actually get N just as we could before. You can, as we defined epsilon in terms of sigma, now you can define N in terms of S. So there's a formula for N in terms of S, and you get S in terms of N. And so you say, so that was Frobenius promonoidal categories. Now I want to talk about star autonomous, and they're more or less the same. It's just that the S should be convergent. And as I say, if A is Cauchy complete, that's not a condition. It's automatically coming from an actual V functor from A op to A. And then when you calculate what the N is, the NA is just coming, it's just A, it's the HOM from I into SA. So a star autonomous V category is really a monoidal V category with this condition at the bottom. Leave out the thing in the brackets in the middle there, and the condition on S becomes, I'm kind of proving it there, that it's saying that HOM B, SA should be obtainable from HOMing out of the unit as HOM I SA tensor B. So that's a condition. You can, instead of putting it in terms of the N, you can put it in terms of this functor S. And of course, that functor S is also determined by its value at the unit, and that's called the dualizing. If you know already that it's closed, then that's called the dualizing object, S of the unit for the monoidal structure. So just a little bit about closedness. Star autonomous V categories are closed monoidal, and here's a little calculation that tells you how to get the left HOM. I'm writing it as LOM. You start with A tensor B C here, And you apply S, because S is a contravariant equivalence. It turns the Hom around, and then you use the condition that is satisfied by S, and then you have a triple tensor product, and you re-bracket it and use the same condition again and bring it out as a tensor in this position over here in the second row of that proof. And then apply the contravariant equivalence again and turns the Homs around, the inverse equivalence, and it turns it into that. So you get this, that Hom A tensor BC is Hom A S to the minus 1 of B tensor SC. And so that gives us a formula for the left Hom. And you do a similar thing on the other side and get the right Hom. And kind of interesting result that is fairly recent, and obviously is begging for other similar results. Michael Schulman proved that you can move from any symmetric monoidal closed category to a star autonomous category. So it's always been a bit of a problem drawing diagrams to represent closedness. You have nice string diagrams and so on for autonomous categories, but for closed ones, you don't. So Schulman's result allows you to move from a closed monoidal category into a star autonomous category, and then use the Girard type diagrams, I guess, in there. I'm not going to do that, but that's a nice result. So the main result, I guess, about convolution for star autonomous categories is that you can the convolution of star autonomous categories is star autonomous, and the formula for the S for the functor category. So if you've got a functor category AX, then it becomes star autonomous by using the inverse of the S on A and then the S on X. And I think I probably won't go through all that proof, but all I've done there is taken the particular case where the domain category A is actually not just, I've said this theorem in terms of a promonoidal, for a Frobenius promonoidal. I think that might be an extension of anything that's actually been published, but it's true. And you can, so the proof that I've got there is just for the case where A is actually star autonomous monoidal category. And that's easily moved over to the case of a Frobenius promonoidal category. So the basic thing to go away from this whole first part is the convolution of star autonomous categories is star autonomous again. In particular, autonomous, which means that each object has a left and right dual. So if you've got a monoidal category, you say it's autonomous when each object has a left dual and a right dual, and sometimes it's called compact, although in the original use of that word, it was the V was assumed to be symmetric, and also the word rigid's used when duals exist. So we say autonomous. But once you have a right dual, you get a V functor from A up to A, which is kind of like the S that we're looking for, and it's an equivalence if you have the left duals. And conversely, of course, if it's an equivalence, then you have the left duals. And this it's easy by the universal property to see that the dual of a tensor product is a tensor product of the duals, just as for adjoint functors and all those other things with adjoints, but it turns around the tensor product, and the dual of the unit is the unit. So anyway, every autonomous V category is a star autonomous, and S is just take the right dual. Okay, so this is a change of complete gear now. I think more or less on, no, maybe a bit. I think this might be shorter than the first part because I've set up the mod, V mod, and so on. So a Mackey functor is I'm going to talk about Mackey functors for groups, and basically mainly just for finite groups. But the idea of a Mackey functor is that it's on the one hand, the generalized representation of G, the linear representation of G, and at the same time, it's a kind of little theory, like a decategorified theory of representations in its own right. So I'm saying that the category rep G, decategorified, is an example of a Mackey functor. And every representation is an example of a Mackey functor. So it was Sandy Green who first introduced, well, it's one of the, I think the first volume of Journal of Pure and Applied Algebra has that paper on where Mackey functors are there. And I'll sort of talk about his original definition, but I can't believe that he didn't sort of know all this category theory, because it's the only way you can make sense of the definition as far as I'm concerned. And so I'm going to try and explain as we did with Alengo Panchad-Sharam in his thesis, talked about how these axioms come to be. So it's kind of, I like it, it's an interesting thing. If you have a co-span, I'm thinking of this actually as G is a group and H and K are subgroups, but this works for any functor, any pair of functors, a co-span in CAT. And if you have a co-complete category X, you can can't extend along I, left can't extend along I, and then restrict along J, and that's the same thing as this is kind of a Beck-Chevalley, a lax 2 version of Beck-Chevalley, that you can form the comma category and then take the restriction along P, the projection onto H, and then the left can't extension along Q, and they are isomorphic. So I'm writing LAN for left can't extension and res for restriction along. And then you can bring it into more group theoretical terms. It turns out this comma category I over G, I don't use the down arrow, I just use the slash for the forward slash for the comma category, and sometimes call it the slice category. And it's a groupoid. The objects are the elements of G, and the morphisms are things that conjugate the elements of G as well, the morphisms, and they conjugate the thing you're coming from into the thing you're going to. Anyway, if you work out what the isomorphism classes of objects of this groupoid are, they're these double cosets. And so I'm writing square brackets K under G over H for a representative class of the double cosets. And when you have a groupoid, it's really a co-product of equivalent to a co-product of groups, where you're thinking of the groups as one object categories. So that's what that sum there represents. The comma category becomes a sum over the isomorphism classes of objects. And so that last formula, because when you calculate the can't extension, gives you this expression of first restricting along I, and then first the can't extending along I and then restricting along J in terms of something else. And then you can calculate what these endo-hom things in I over G. Oh, I've got a downward arrow there. Okay, it's a comma category. It turns out you can express it in terms of either H intersect the conjugates of K or the other way around. So you get these two expressions, and so these two things must be isomorphic, and that's an important ingredient. This restriction along that isomorphism between these two conjugate things comes into this formula by using So IND now is what representation theorists call left Kant extension along the inclusion of a subgroup, where the subgroup is written at the bottom and the top, the two subgroups. So that's left Kant extension along the inclusion of this in that, of conjugate of G conjugate of H intersect K into K. And so you get this formula, and that's called the Mackey decomposition theorem in representation theory. So it's just a matter of interpreting usual category theory. That's the thing to take away, just interpreting usual category theory of Kant extensions in terms of this group case. And so here's this big definition that you'd have no hope of understanding, I think, unless you knew that bit of category theory behind it. But of course, the group theorists, the representation theorists think otherwise and have their own ways of understanding these things. So a Mackey functor for a group, G, assigns to each subgroup of the group a vector space, and then to each subgroup of that subgroup, something that looks like Kant extension along the inclusion of K and H, and something that looks like called T. They call it T because they use the words transfer or trace for that operation as well, and something like restriction, which goes in the opposite direction, goes back from MH to MK. And then these little things that you might not understand where they came from are all because of those isomorphisms between the conjugate things. And so they raise their hair. The first couple of axioms are kind of functoriality things. There's compatibility of these linear isomorphisms, and then compatibility amongst themselves. But the main axiom is this 4, which is exactly that Mackey decomposition theorem, put in terms of these sort of decategorified notions. Okay. And the other thing to understand, there's also something called a green functor, which is a Mackey functor with a certain property, and that really comes from Frobenius reciprocity, which is something about the interaction of the tensor product from a categorical point of view. That's the interaction of the tensor product when you're dealing with monoidal categories with the Kant extensions. So there it is. That's the axiom. Well, that's the what I call Frobenius reciprocity. IND, remember, is just the representation theorist's word for left Kant extension. Whoops. So a green functor is a Mackey functor such that everything, well, so that assigns an algebra rather than just a module or a vector space. And all these structure things become algebra morphisms, and you have this Frobenius reciprocity on both sides. So that's how I kind of understand green functors. Although we'll get a better understanding soon, I hope. So examples of Mackey functors, each representation gives you one. If you take the green definition there, by taking each subgroup of G to just the G set morphisms from G over H as a G set, one of the indecomposed, the connected G set into R, and you get the variation, the functoriality from the representation. The representation is just a functor from the one G regarded as a one object category into vector spaces. So it's a vector space with actions by the elements of the group. So that's why I say every representation becomes a Mackey functor. But then the sort of the theory of representation becomes a Mackey functor too, but by assigning to each H the category of representations, the Grothendieck category of the category of representations of H, of the subgroup H. And from one of the applications of Mackey functors has been into number theory. by these authors down here in 2001. But they needed, for the infinite case, where if you're doing Galois, I mean, you may see immediately that there's a connection with Galois theory because we're looking at the subgroups of a group. So by the fundamental theorem of Galois theory, the subgroups are the same as extensions of the field and so on. So that's how it gets into Galois theory, and that gets into number theory. But they needed to modify it if you have an infinite group, or when, in the case of Galois theory, you need a profinite group, and they have applications there. So Green already realized that he was dealing with two functors, really, when you were dealing with a Mackey functor, a covariant one and a contravariant one. And he gave the definition in terms of two functors on connected G sets. Connected G sets are the ones that are of the form G over H for a subgroup H, the transitive including it. And then Dress made it into something that we can make much more categorical by using the fact that the G sets is really just the finite coproduct completion, and they're not the finite coproduct completion of when you're dealing with a finite group G of the connected G sets. And so rather than work with G and G sets, you can now talk about a category E, which is going to be a little bit like G sets, but more categorical thing. And you can then define what you have, what you mean by a Mackey functor on E rather than on G. And this was done, well, where am I here? I guess this was done by Dress, yes. So a Mackey functor consists of two functors, one from E into vect and one from called M lower star, one from E op into vect called M upper star. And they agree on objects. This will be very familiar to people who nowadays, I think, this kind of thing, but they have this Beck-Chevrolet property, but it's called a decategorified version of it because these M's of things are not categories, they're just vector spaces. So if you take a pullback, then that turns all the arrows around if you will apply M lower star, but if you apply M upper star, you get them back the other way. So you want that square on the right to be commutative. And you also want every coproduct diagram in E to turn into, when you apply M, you use the M lower star and the M upper star to get you a situation which could be a direct sum, and you ask that should be a direct sum. So then Harold Lintner got into the act, category theorist, German category theorist, and realized that these were really defined on span. So take V to be, I'm going to take V to be a fixed thing now. It's the closed monoidal category of commutative monoids, abelian monoids, if you like to call them that. So categories enriched in that are very much like additive categories. The products, finite products, are the same as finite coproducts. And E will be a Lex-tensive category. What that means is that you have finite coproducts and finite limits, and that E over X times E over Y is equivalent to E over X plus Y. And this is terminology of Chagnol and Levere, I think. Although, yeah, and Robin Cockett has done a lot on this with Steve Black. So anyway, let span E denote the V category. I'm not considering span E as you people who are used to two categories. I'm just considering it as a category at the moment. So span E, the objects are objects of E, and the morphisms are isomorphism class of spans. And you compose them in the usual way by pullback, and that induces the right thing on the isomorphism classes. And this Lex tensivity is used to show you that the co-product is actually the co-product in span, but it's also the product, because span op is actually the same as span, just easy to see. And so the co-product is the same as the product. And so you have direct sums in particular in span E when you have an extensive category. But span E is actually a monoidal category as well, and that's where the product in E comes in. The product in E makes span E into a symmetric monoidal V category. And not only that, you have, in the same way as with mod, you can regard every arrow in E as a span by putting the first map of the span to be an identity, and you can go back the other way by putting the second map in the span to be the identity. And these lower stars and upper stars are very nicely named because they're exactly they exactly give you the upper star and lower star on the Mackey functors that we're looking for. So every and the other point about linking up, this is the first link up with Frobenius things, is that every object of span E is actually a Frobenius monoid. So each thing is its own dual. You're probably familiar with that. It comes from that duality I mentioned on the last page. So in particular, span E is autonomous. Every object has a dual. It's just itself. And Lintner's little paper, which I think was quite nice, recognized very early in the piece, 1976, that Mackey functor is really just a V functor. Well, see, the V functor incorporates, he didn't quite say it this way because he wasn't using enriched categories, but the V functor gives you that preservation of the direct sums, or taking, well, it's preservation of direct sums. In the old way of saying it, you didn't have direct sums in the domain because you were looking at E rather than span E. So, yeah, the old M and lower star and upper star are just the composites with the usual lower star and upper star. Excuse me. So we let Mackey E denote the V functor V category from span E to vect. And it's a symmetric closed monoidal category by convolution. And there's the formula for it. Yeah, it's fairly easy to see that the usual convolution formula, because the main thing is monoidal, just comes down to this. And the unit for that is called the Burnside functor. The value at X is the free vector space on the commutative monoid, where you make the E over X into a commutative monoid under isomorphism classes of co-products. And it turns out the green functors are just the monoids in Mackey E, so they become monoids. So you can do a few different things here, but I've just chosen to take the simplest one. We'll look at the functors into finite dimensional vector spaces rather than vector spaces, and I'll call those finite Mackey functors. So you call it a finite Mackey functor when every mx is a finite dimensional vector space. And here's the theorem that if you have an extensive category for which every object is a coproduct of objects from a given finite set of objects, like in G set, then Mac finite E is closed under the symmetric monoidal structure on Mackey E, and then because of the that theorem on convolution of star autonomous categories. In this case, we're dealing with very simple star autonomous categories because both the domain and the codomain are autonomous, and there's a little complication because vector's not co-complete. So you've actually got to do this convolution in the full vect, not in finite dimensional vect. And so that's why I've talked about it being closed under the closed monoidal structure. But you do the promonoidal tensor product, the convolution tensor product using the full vect. Yeah, the point is that co-products mentioned become direct sums in span E, and so are preserved by the Mackey functors, and the HOMs in span E become finitely generated commutative monoids. And this means that the coends and ends involved in the convolution structure can be calculated over a finite category. So another thing you could have done is to take a nice star autonomous category containing the full vect, and that's probably something that should be looked at more often in linear algebra, a star autonomous completion of just ordinary vect. Now there's some work by Tembara. It's amazing how many times Tembara's work has overlapped with our stuff. To look at the monoidal center, if you've heard of that, that's a way of getting a braided monoidal category out of any monoidal category. And he's got a nice result there, just in the case of where E is G sets, finite G sets for a finite group G. If you take C to be the connected G sets, then, well, one of the results that Brian Day and I had was that the center of Mackey is actually a V functor again. It's a more general result, but applied to this case, that if you take the center of in certain conditions of a functor category, you end up with a functor category again. But Tembara went further, and this gives you a kind of excuse for extending the notion of Mackey functor beyond just groups and categories of the form G set to other categories, because it turns out you can actually prove that the monoidal center of finite G sets is again a category of Mackey functors on something, and not just another functor category. And that's quite a hard proof, and I think it probably can be generalized to a more categorical theorem, but I quite like that. So I think my time's, oh no, I've still got a little bit, sorry. Just to show you about the generalized representations. So I think it's a good justification for the fact that we should think of a group as being a one object category after all, although a lot of people have poked fun at it, because you can often generalize a lot of things that actually just come up when you're still interested in just ordinary group representation theory, where you're looking at functors out of other things like span G sets and so on. So you can extend the category of representations to the category of Mackey functors, finite dimensional Mackey functors, and it preserves everything. So you get this functor from, well, you get a functor from finite dimensional representations of G right down the bottom there into Mackey functors finite G, and it comes by the usual Kahn process by a certain functor from span on G sets finite opposite into representations, and then you do the fact, because you can just swing it around. I think you get the idea that yeah, every finite dimensional representation can be regarded as a finite dimensional Mackey functor, and it preserves all the structure, everything. And so the only little problem is that the codomain there is only star autonomous. But it's a very nice star autonomous. It's got some special properties. The S is its own inverse and things like that. So it's not that much worse. The representation category is autonomous, of course. Okay, well, I think that's it. And Sorry, I probably went too fast, but thank you very much.
Thank you, Ross. Join me in clapping for Ross.